So we're going to talk about segmentation. I'm going to be focusing on hidden Markov models for the afternoon. So this is kind of an outline of what I'm planning to go through. First of all, kind of going over what segmentation is, and then a little bit on discrete time random walks. I think you guys covered a little bit of some of this stuff this morning. And then hidden Markov models. And then I have 3 potential tutorials. I'm not sure what we're actually going to have time to get through today. It's possible that this stuff we won't have time for, but I don't know if there will be time later in the next week or so, but I guess we can see. Oh, and I also just wanted to give some appropriate credit. These slides are adapted from Tiramisha, so they're not 100% my work. Okay. So what I'm going to be talking about, or meaning when I say segmentation, basically what I'm talking about is identifying track segments that underlie different behaviors of the animal. And so what we're going to be assuming is that different behaviors correspond to different, or manifest of different movement patterns. So this is an example of kind of a time series of step lengths, and you can see there's kind of times when the step lengths are bigger and times when the step lengths are slower. So we're going to be kind of assuming that those are different behaviors of the animal. And so one example might be an animal that's switching between kind of an encamped or a very slow and non-directed movement and an exploratory state. So something that's fast, more directed. So that would look something like, sorry, that's probably hard for you guys to see, but an encamped state with really slow step lengths and kind of not a lot of concentration on the turning angles. And then the exploratory would be longer step lengths and more directed turning angles. So I guess why we might want to do this is we want to understand kind of the when, why, and where of animal behavior. And so we kind of want to know what's driving these different switches between the behavioral states. So kind of what variables, maybe it's something environmental or something to do with the animal. And then we might also want to kind of map out where they're engaging in those different behaviors. Okay, and so there's different ways to segment your data. It's usually based on metrics such as these, so we might have something representing speed, so the step length or velocity, something representing kind of the directional persistence of the animal, so something like the torque velocity or turning angle, and then there's also other metrics that you guys talked about today, like first passage time and mean squared displacement. And so using these different metrics, there's different methods that can be used. I think last year, change point analysis was discussed a lot. I think you already talked about that, so that's not something that I know about, so I'm not going to be covering it. I think it is available with the Animove 2024 materials. And then there's other methods like classification and clustering. What I'm going to be talking about is specifically hidden Markov models for this purpose. And this is just a review paper that covers all of these methods and kind of outlines what they are and what they're good for, etc. That I found useful because I didn't actually know about a lot of these methods. I've always just used HMMs.
Yeah, because like we want to be in Costa Rica again. We don't hear well. It's a bit tricky to hear you with the 2 AC on. Yeah.
Okay. I mean, I can try to talk louder.
No, I think
okay. I missed my spot in Canada back there. I was being like blasted with AC and I liked it. It's really hot up here. There's no. Okay. Thank you. So this is just kind of a very brief overview of what HMMs are. Kind of what we're assuming is that there's some behavioral state that's unobserved, so we don't actually have data directly on the behavioral state. We have observations that we can link to those behaviors or derive those behaviors. And so basically we're going to have some state-dependent movement model, so a movement model that kind of switches between different states. And so sometimes I think an HMM is called like a dependent mixture model, where it's kind of this a clustering model, but that also accounts for this temporal dependence. And so we're acknowledging that it's this time series, and we're going to model that directly. And so with like a standard clustering without any temporal dependence, this might actually be in a different state. The HMM is going to take into account that it's not likely to keep switching in and out of states at every time step. And so these are probably, as most of you know, these are pretty common in movement ecology now. oh, I guess I didn't really say this, but if at any point, like I'm going too fast, or you want me to cover something again, please just, I don't know, signal or hold up your hand or something. It's always hard to know exactly what speed to go and how to pitch things. So if things are too technical or you need to like go over something again, just don't hesitate to ask me to. Okay, so I was going to cover a little bit of discrete time random walks. This is kind of the foundation of the HMM. Sorry, I'm like fiddling with the microphone. It's probably going to sound really bad. Okay, so this is a discrete time model. So we're basically assuming that we have locations at a regular time interval, so times t1, 2, all the way until time t. And so basically we want a model typically that's going to capture both the speed of the animal and the directionality or the directional persistence of the animal. And so I'm just going to discuss a few random walks, starting with a simple random walk and kind of building up from there. Okay, so the first that we might consider is just a very simple random walk, where basically we assume that, or it only considers speed. So the direction is going to be completely random. I think this was talked about a little bit this morning with Brownian motion. So a Gaussian random walk in discrete time, we would assume that the location xt is a random draw from a normal distribution centered on the previous location. And so then the standard deviation of that normal distribution is going to be a metric of speed. So as it gets bigger, the steps are going to be longer. But there's no directionality in this model, so it's only based on speed. Another way that we really commonly write random walks, and that's going to be important, is to write it as a probability distribution of step lengths. So that exact same model, that Gaussian random walk, can actually be represented as a Rayleigh distribution of step lengths, where it's still the same model, but it's just kind of a different representation where each step length is a random draw from that Rayleigh distribution. If you don't know what a Rayleigh distribution is, that's fine. We're not going to talk about it again. And it can be any other distribution that has the correct support for step lengths. And as was kind of discussed this morning, that isn't a very realistic model of animal movement, and so a better model is going to be a correlated random walk. And so that's going to capture both the speed and the directional persistence of the animal. So this is an example of a realization of a random walk. It's just kind of scattered all over the place, whereas this is a correlated random walk, which looks like a more realistic animal trajectory. And again, this is one way to kind of to represent it is in terms of the distributions of step lengths and turning angles. And this is what we're going to use for the HMM, so that's why I'm showing it. So this would be an example of a step length distribution, gamma distribution. This is just different parameters, so kind of different movement speeds. And then a von Mises distribution of turning angle. I'm going to talk about these a little bit more because we're going to use them over and over again. So yeah, we can assume that our step lengths come from a gamma distribution with parameters mu and sigma, where mu is the mean step length and sigma is the standard deviation. And turning angles, a really common model for this is the von Mises distribution. So basically, there's two parameters for the von Mises distribution. There's a mean, so that's going to be the mean turning angle. So when it's at 0, that means that they're going in the same direction that they were at the previous time step, so it's directional persistence. And when it's at pi or negative pi, it means that they're completely reverting in direction. And so this is, I'm not showing it on the circle, this is actually a circular distribution, so it actually wraps around, negative pi and pi meet. And then the parameter kappa is the concentration parameter, so that just kind of gives the variability around that mean. Kind of like a normal distribution has a standard deviation. And we're not actually going to talk about this in detail, but another random walk is a biased correlated random walk. And so that's an extension of a correlated random walk where we not only have speed and directional persistence, but we can also have some sort of directional bias towards a target. And so this is an example of what that could look like. So they're kind of biased towards, this is their colony, and they're kind of going out towards their foraging site, and then they're going back. So there might be some sort of bias towards that colony in different movement states. I feel like I went through that really fast. Is everyone following? Okay, I can slow down a little bit.
It's hard, I will be super honest. It's hard to listen the end of your sentences. This is what I'm struggling, but I missed just the last sentence.
Okay.
I don't know if that's you. Yeah, you can tell me.
I think the most it goes a little bit lower at the end of your sentence.
Okay. Now I'm gonna start like yelling at the end of my sentence. Okay. Is there anything in particular that you guys missed or want me to go over again? Is the idea of a random walk and a correlated random walk, does that kind of make sense? What we're
Yeah, if we can go back to the von Mises distribution,
Yes.
I got lost there.
Okay, yeah, that's fair. So the von Mises distribution is a circular distribution. So it's basically analogous to a normal distribution on a circle. And so we have a mean parameter. And so that's going to be the mean turning angle. So you guys covered turning angles. So you should know that a turning angle of 0 means that they're going exactly the same direction as the previous time step. So that's perfect directional persistence. And when they turn around, it's going to be a turning angle at pi or negative pi. Does that make sense? And so then the von Mises distribution has those two parameters. The mean, we usually expect that it's going to be 0, which means that they have some sort of directional persistence. So, it could be something like this, where the mean is 0, but it's like really spread, so it is quite random. And it could be all the way to something like this, that's centered on 0, and it's very peaky, so they have a lot of directional persistence when it's more peaked.
Maybe you can explain why it is important that there are these parameters. I mean, you did just now, but I think the point really is that because there is a formal distribution, there are parameters which then you can statistically estimate. Okay?
Okay, yeah, so the idea of like a probability distribution is that maybe, yeah, okay. Did it make sense for, yeah, sorry, go ahead.
So in that regard, should you be checking that your data is distributed like this before you even attempt to do it in the markup model?
Well, I mean, kind of by nature, your turning angles are, they might not be captured super well by a von Mises distribution, but it is one of the suitable distributions because it is a circular distribution. So it accounts for the fact that a turning angle at pi and negative pi are basically the same thing. They either went all the way to the left or all the way to the right. And so there's only kind of a few of these raft distributions. It could also be something like a raft Cauchy. But yeah, I guess kind of like, sorry, maybe that wasn't a very super good answer, but kind of by looking at your data, first of all, we know that step lengths are going to be 0 bound, so we don't want any distribution that's going to have any support for negative values. So something like a normal distribution isn't going to work. We're never going to have negative step lengths. So it always needs to be a positive only distribution. And then exactly which one of those ones might depend on what your data looks like. So something like an exponential distribution doesn't have the flexibility to take all of these different shapes. It's always going to look something like this. Whereas the gamma distribution is quite good because it can take anything from that looks really exponential to something that looks almost like a normal distribution but bound at 0. Does that kind of make sense?
Yeah.
So yeah, it depends on, we're just talking about step lengths and turning angles. It depends on exactly what your variable is, but you're always going to want to find something that has the correct support for your distribution, so the correct range of values, and then that you think has the flexibility to capture the shape of your data. Okay, can we get into the fun stuff, the HMMs? Okay, and so what we're going to do in an HMM is basically to have this multi-state correlated random walk. So we're assuming that the animal switches between several correlated random walks, trying to do the end of the sentence. No, it's fine, it's all good. So this is an example of what that might look like. We have this blue state here, which is very slow, kind of all clustered together, and then something like this second state, which has a lot bigger step length and is a lot more directed. Okay, so this is the basic dependent structure of a hidden Markov model. So as I kind of mentioned, we have, so it's this doubly stochastic process. So we have two processes that we have to work with. First of all, we have an observation process. And so that's kind of represented by these arrows going up here. And so it describes how the behavioral states give rise to the data. And I will go over exactly what these models are, but it's just kind of the overview at first. So we need to define a model to describe that. And then the second part of the model is the state process. And so these states, like I said, are unobserved. We don't actually know these states in our case. And so we need a model that describes how the animal switches between the different behavioral states at each time step. And so that's why it's doubly stochastic, because there's two kind of probabilistic models happening at the same time.
So can you put an example of an observation and a state process? So the state process is like the changing, no? From one observation to another.
The state process is so the states are unobserved, so those aren't our observation variables, so they're not our observations, so they won't be like our step lengths or turning angles or anything like that. The states are like foraging or traveling, something like that. And then there's going to be a model that describes how the animal is switching between those different behaviors at each time step. I will describe this all in much more detail. And then the observation process is going to be something that describes how the behavioral state gives rise to the observation. So that's basically what we're assuming, is that there is some true underlying state that we don't see, and that gives rise, that's why the data looks the way that it does. So it gives rise to the data. Okay, so I'm going to start with the observation process. So this would be the actual data that we have. So we can define the observation variables as our step lengths and turning angles. That's going to give us a way to have the observation process as a correlated random walk. And so basically the observation process is going to be defined as these state-dependent distributions. So state-dependent probability distributions, like I showed, the gamma distribution, the von Mises distribution. And so you basically want to pick a distribution that's going to be sensible for each of your observation variables. And so basically we're assuming that when the animal is in state J, state 1 say, the observation variables are going to be random draws from those probability distributions with some parameters theta j. Seeing a lot of confused faces, but hopefully it will become clearer. We're going to keep going through this. And so we're going to use this to specify a multi-state correlated random walk. But an HMM is just a really general model. This could be for any data, any observation model. So this is an example, and this is what we're going to kind of work with continuously throughout this. So like I mentioned, you can specify a correlated random walk in terms of distributions of step lengths and turning angles, and so that's what we're going to do. We can define that the step length comes from a gamma distribution, and the turning angle comes from the von Mises distribution. And so this would be an example of, say, a two-state model, where one state has a step length distribution that looks like this, so it's capturing most of these short steps. And then the second state has kind of a longer, captures more of the long steps, so that may be slow movement and faster movement. And then same for the von Mises distribution. Those long steps might be associated with a lot of directional persistence, and the short steps might be associated with very kind of more random directions, which would correspond to something like resting or foraging. Is this kind of making sense?
Maybe if you say, because this is super important, if you say it one more time, like this step and turning angle, the two kind of distributions, what they, you were saying, what's the percent?
Okay, so maybe this will help.
Just said now, yes.
So basically what we're assuming with this is that, so when the animal is in state 1, their step lengths would follow this distribution. So if you were to like randomly choose a step length from there, you'd be more likely to get short step lengths because they're more likely to have short step lengths when they're in state 1. And they would have, a lot of kind of random directionality. And then so it would be the same for state 2. So it's kind of what we're assuming is that these probability distributions are models for the movement in each state. Yeah.
Do your data focus on step length, structure, and angle, or do you focus on both at the same time, all the time?
Both at the same time.
I guess the question again about should our data then have this distribution, and is that something we use to be checking?
So, Chris, you have a thought? Yes?
Well, we can do model selection, we don't have to worry about that.
I think
I don't think you need to fit a gamma distribution before fitting this model. That's not a part of, yeah. You could compare HMMs with different observation distributions. So you could choose a gamma distribution and compare it to, I don't know, an exponential distribution or something like that, and you can compare which model fits better. But prior, you should look at your data and think about it and think about what types of values your data takes and what probability distribution is kind of appropriate for it. But I don't think you need to go through a step of fitting distributions, because this is fitting distributions, the HMM is fitting the distributions.
I think they're just used to fit distributions and do model selections before, and I think that's why people are
Yeah.
thinking this is something that we have to do.
No, I would say no.
You can do that.
I don't think you need to though, because your HMM is fitting the state-dependent distributions, and so
You can have different, you can do model selection between HMMs.
you can do model selection between HMMs. I think people are often used to fitting distributions before fitting their model. So they're is my data normal? Is it gamma?
Oh, okay, maybe I'm misunderstanding.
For a GLM or something, people I think often if they want to use a gamma GLM, they'll fit a gamma distribution to their data first.
No, it's not.
But people often do that.
You shouldn't do that.
And I'm just saying that no, you don't need to do that. The model is fitting the distributions, and you can compare those models once you have them fit.
Yeah.
Yes, I think we're on the same page. Okay, and I kind of already mentioned this, we're focusing on step length and turning angles, but you could also incorporate any other data that you have. So you could have stuff like the depth of your animal, the acceleration, posture, heart rate, basically different variables that you think are important for the behaviors that you're interested in identifying. And so, I'm not sure if you guys can see this, but this is an example of what that might look like. This is a state-dependent distributions for step lengths, turning angles, and then there's an additional data stream for the dive depth. So this can help if you have, say, two behaviors that look very similar in terms of movement speed and directional persistence, but maybe one they're at depth and one they're at the surface. You could distinguish them that way by adding another data stream. Okay. So are we kind of all on the same page for the observation process? Okay. Oh, thumbs up. Okay. Okay, so the kind of second process within the model is the state process. And so basically we model the state process as an unobserved Markov chain. And so a Markov chain is basically the stochastic process that assumes that the state at time t only depends on the state before it. So there's some switching happening at this state or at this time step. And so basically that's saying that st plus 1 doesn't depend on st minus 1, it only depends on the state before it. And so it's been described as like a memoryless process. And so basically the behavioral switching at each time step is defined or governed by these transition probabilities. And so this is a matrix that shows the probability of staying in state 1, because it's a switch from state 1 to state 1. And then the probability of going from state 1 to state 2, all the way to state 1 to state k, where k is the number of states that you have in your model. So it's a matrix that has the probability of switching between each set of states in both directions. And so actually we only end up estimating less transition probabilities than we have, because basically if we have 2 states, we know that, say this is foraging and exploring. If we know these 2 transition probabilities, they have to sum to 1, so we know these transition probabilities as well. Okay, does the state process kind of make sense?
Can you repeat the very last thing you said?
Oh, it's just a little bit of a minor point. When we estimate it, we actually only estimate less transition probabilities than we actually have. So for a 2-state model, because the transition probabilities have to sum to 1 across a row, so if you know that this transition probability of going from exploratory to foraging, then you know this transition probability as well. So it would just be 1 minus the other transition probability. Yes.
A little bit, maybe I went a little too heavy on the equations, but hopefully as we go through, you'll kind of develop the kind of more ecological intuition of why we're doing this and kind of what it all means. Can I start? Okay. Okay, so I'm just going to go over a couple important assumptions. There's more assumptions than what I have here, but these are just a couple. So HMMs are scale dependent. I think this was talked about quite a bit over the last couple of days. Basically, we need the observations to be at the same time interval. So either we have 2-hour data, we have 5-minute data. Each observation should have the same time lag between them. And so this is an example. Sorry, I should have both of them up at once. It's an example where it's the same underlying movement process. So that's kind of shown by the black line underneath. And this would be the kind of realizations from that at a given time interval. And this would be at a much bigger time interval. And so, I mean, as you can see, as you increase the time interval, your step length is going to increase. Your turning angles are generally going to become less directed as the time lag increases. And then there's also implications for the state switching dynamics as well. If you think about if you have a 10-hour observation, they're more likely to have switched out of the, and so that's what this plot here is showing is the dwell time. So it's the number of observations that are going to be within a state. So as that increases, you're going to have less observations in a row in that state. Does that make sense? Oops. And so that's a result of the transition probabilities. Transition probabilities within the state, so the state persistence decreasing as, sorry, this plot is showing the opposite of what I'm saying. So this is showing the transition probabilities of switching out of a state, so from 1 to 2 and 2 to 1. And as you increase the time interval, that transition probability increases. So they're more likely to switch out of a state as you have a longer time interval. And so there's implications for both the observations and for the state process for scale dependence. Okay, and so one challenge that kind of arises from this is that we should have data that's at a regular time interval and that has negligible error. I'm kind of throwing these in together. But often that isn't the case. I'm sure probably many of you know we often have missing locations or we have a lot of measurement error. And so some solutions, I'm not going to really go through these in detail today, but if we just have a few missing observations, we can just ignore this if they're not like a huge, like many successive in a row. But they still need to be in the data as a row where the observation variables are NA. And so the HMM can deal with that. If we have a lot of missing locations or many in a row, or we have really noisy locations, a really common approach is to filter the noise and regularize the tracks using a state space model. And so this is an example of that. So this is a track where we have a bunch of missing observations. So we kind of have these funny looking, huge gaps. And a state space model will basically give us a way to predict locations over that gap. And then we can use those, that regularized track in the HMM to define our behaviors.
Maybe one question, when you say some, is there a rule of thumb of what is acceptable and what is not? Like some missing observation. Is there any, because we don't know anything at the moment, so some. Maybe we
Yeah, I feel like I'm not going to have a super satisfactory answer to that. It probably depends a little bit on how much data you have. I mean, like, I wouldn't keep more than like maybe 3 locations back to back to back. Although it depends on the resolution of the data. I don't know, it depends on a lot of different factors. But yeah, like a few here and there, I think it's not a big deal to kind of just have as NAs. And it's basically going to assume that the transition probabilities just remain consistent over those missing observations. But no, sorry, I don't really have for a lot of this stuff, there isn't going to be hard and fast rules, which I realize is not always super helpful, but.
But is it the case that maybe multiple locations, like multiple missed locations, one after the other, maybe it's more problematic than
I think,
missed locations through time, like more spread across time? What's more of a problem for hidden market models?
Yeah, so say you have like 1,000 data rows and you have, I don't know, 50 of those missing in a row. I think that's a bigger problem than 50 kind of missing randomly. Because then you're going to be assuming that the state process is evolving over those 50 rows where you have absolutely no information about what's actually happening. And so typically if you had something like that, you might actually just split the track. So you would then have the same individual, but maybe you have 2 tracks for that individual instead of just one. Yes?
So in the package, it's
Okay. Okay, so one option so one problem with doing this is when we impute locations, so we predict the missing locations and then just use those in the HMM, you're basically assuming that those are accurate. So we're assuming that there's no uncertainty on those predicted locations when actually there is. And so one option is to combine or to try to account for that uncertainty with something called multiple imputation. I think I saw your hand.
Yes, we have to always look this like a step. First, trying to the first option, if not the second, or we can prioritize which solution. Like,
Pardon? Sorry.
There is a priority in the solutions. Like, this is the best option, or directly, or we have all the ways to do that.
I'm sorry, I'm not sure.
I think it's about imputation of the missing locations of what should be the best, your options.
Oh, this is kind of the same question that I got before. I don't know. I'm sorry. I don't have like a hard and fast rule of when you should do one or the other. If you have a lot of measurement error, it probably is a good idea to use a state space model to try to account for that measurement error and to get the more likely locations. For missing data, I guess one thing to mention actually for imputing locations, so predicting something like this, is it does tend to be a bad idea to do it over a long gap. So if you have like 100 missing observations, if you use a model to predict those, you're just going to predict a huge straight line. And so what's better to do actually would be to split it into multiple tracks and then fit a state space model to each of those track segments and predict those locations. Does that help? And so what multiple imputation is going to do to try to account for this uncertainty is from the state space model, you can generate a whole bunch of plausible movement tracks from that model. This is just going to give you like the most likely location, but you can also predict a whole bunch of plausible tracks from that model. And so then you fit an HMM to each one of those tracks. So, sorry, this would be an example of a whole bunch of predicted tracks. So this is where there's gaps. As you can kind of see that there's many plausible tracks that the animal could have taken. And so you would fit an HMM to each one of those tracks, imputed with the state space model. And then there's a way to combine the results from those HMMs to get a better estimate of uncertainty. So it accounts for the fact that we don't actually know what the animal did here. This isn't actually something that I'm going to talk about in detail today, but it is something that you can do if you have a lot of missing locations or measurement error. Okay. So a second assumption is that is basically, I mean, this is kind of a bigger assumption with segmentation in general, but basically we're assuming that behaviors actually can be represented as discrete states. And so I think this is a little bit more of a conceptual distinction, but I think some people like to think about behavior as kind of being a continuous thing, so it's not just like they're switching from fast to slow, there's some kind of continuous spectrum of that. And so this would be an example of something called a move persistence model, where it's occurring along this continuous spectrum, where persistence is kind of how directed that movement is. And then again, you could also think about modeling the movement speed as a continuous function instead of something with discrete state switches. We're not going to talk about these approaches, it's just to kind of illustrate that we are making the assumption that there is discrete behaviors.
Can you remind us what the resistance is?
Persistence?
Yeah.
So directional persistence would be if they're moving in the same direction, but you could also have persistence. I think this model actually accounts for persistence in both the speed and directionality of movement.
Persistence in one of the speeds.
Yeah. Usually I'm going to be talking about directional persistence. Yeah. And so if we assume that we have those discrete behavioral states, one thing that we have to choose is the number of states. And so we have to do this before we fit the model. And so this is something that we choose. And so most studies use somewhere between, I mean, here I said 2, but 2 or 3 is, I think, kind of most common. Once we start getting into a really high number of states, it gets really difficult to actually interpret them biologically, unless maybe you have like tons of different data streams. So if you have step lengths, turning angles, dive depth, heart rate, then maybe it starts to get a little bit easier to differentiate those behaviors. But generally, when we get into those really big number of states, it's really hard to actually interpret what those behaviors are.
Do you use acceleration?
You could use acceleration. Yeah. And so typical model selection tools like AIC or BIC aren't really used for the purpose of selecting the number of states, because they really tend to favor models with more states. And it probably is that model is slightly capturing the data better, but it's not really an interpretable model of behavior anymore. So generally people don't use AIC or BIC for selecting the number of states. You can use it for other types of model selection, like choosing between distributions or variables or covariates.
BIC gives you 2 complex models.
Yeah, they tend to favor, like if you give it a 6-state model, AIC or BIC will more commonly.
Well, AIC, yes, but BIC in theory is supposed to give you the.
Yeah, I think.
Yeah, it's just like 2 times.
Because reality is too complex.
You can't use AIC or BIC for picking the number of clusters. It's too good over.
But AIC is sure, but I mean.
BIC is not that conservative in the classification.
So there's a paper by Pol et al. That looks into this, and I think they do show that BIC does tend to select too many states. Jordan's not listening. And so what they recommend to choose the number of states is to use a combination of model checking. So, I mean, we'll get into what I mean by that, but there's certain things that we can look at in model checking. And then also biological knowledge. So if we can actually interpret the states as something reasonable biologically. And so this is a nice paper that kind of outlines that process a little bit more. And there's also work being done using penalized likelihood methods. So this is meant to be a way to kind of choose the number of states automatically during model fitting. I don't know all that much about it. This is a brand new paper that just came out in 2025. As far as I know, it's not really like widely available in any software packages, but maybe one day. I know biologists always want like an automatic way to choose the number of states. So maybe we'll get there one day.
But maybe it's about choosing the number of states. Then you also have to define states, right? Like, I'm just wondering, do you start from the biological and behavioral knowledge of the animal, or do you start from the data and all the parameters we calculate, like turning angle and step length? Like, how do you combine these two to get to the number of states and what these states are in terms of behavior?
That's a good question.
Step back.
No, so one thing that's important to note is that before you fit the model, you don't know what the states are going to be. I think it's really common for people to want to say, I'm fitting an HMM that includes foraging and exploratory behavior. But you don't actually know until you fit the model and you look at the outputs if that actually makes sense. And so you might choose a number of states that corresponds to behaviors that you think the animal is going to be engaging in. And so you might try a 3-state model and see if that kind of aligns with what you thought before. But yeah, you don't know the states before you fit the model. That's an important point that. Okay. Yeah, so then I guess choosing the number of states, you might be like, well, I think that, there's maybe 3 behaviors that they might be engaging in, and so you might fit a 3-state model. Maybe you see that it does look like the behaviors you were hoping to identify. Maybe it looks completely different, or you need to change something, go down in the number of states. But yeah, it's kind of, you do need to like look at your model outputs and see if they actually make sense in terms of biological behaviors.
So can you look at sort of a couple of different options, the number of states, and just see whether they align biologically with what you think is plausible? Is that just a trial and error rather than any model selection process? Yeah,
totally. You could try a 2-state model, a 3-state model. What did I say? 2-state, 3-state, 4-state. Yeah.
What are the most common? Like 2 states would be like correcting or resting or something? Or
Yeah, I mean, typically if you fit a 2-state model, it's really common that it's going to be something that looks like a slow, undirected movement state and something that's a faster, more directed movement state. That's really, really common. Then when you start getting into 3 states, it's, again, usually clustered by slowest movement, kind of intermediate movement, fastest movement. I mean, this isn't always going to be the case, but this is kind of the most common. And then what exactly that means for your animal is kind of up to you as the biologist to interpret. Yeah. We will cover this a little bit more. Okay. So I'm going to talk a little bit about inference for HMMs. So this is how we actually estimate parameters. And so basically this is kind of our setup. We have our data, we have observed step lengths, observed turning angles, and basically what we want to do is estimate all of the parameters. So we have transition probabilities that we want to estimate, the observation parameters, so that's the parameters of the state-dependent distributions, so the mean of the step length distribution, the variance, and likewise for turning angles. That's what I'm calling theta. And then there's also something called an initial distribution that I'm not going to really talk about because it's not a very important parameter. The initial distribution. There's also something called delta. It will come up like in the code when we're looking at the outputs, but I'm not really going to talk about it. And so I'm not sure how kind of familiar you are with the concept of a likelihood function. It's basically a joint probability of the data given the parameter values. And so it's the likelihood of the parameters, or the probability of the data, sorry, given these parameters. And basically what we want to do is we want to find the set of parameters that maximizes the likelihood of the data. And this is the maximum likelihood estimators. You don't really need to understand the details of this. Oh yeah, I guess I kind of mentioned this. Delta, sometimes we fix it, but I'm not going to really talk about it. It's not super important. I guess to quickly define it, delta is the initial distribution, so it's basically the probability of being in each time step, or in each state, sorry, at the first time step. So it's a pretty minor parameter that we're not going to really talk about. Yes?
You don't take that to be the steady state distribution?
Yeah, I guess if you don't have any covariates, it would be the stationary, the stationary distribution. But even when we have covariates on the transition probabilities, it's pretty common to fix it, and you can just assume that it's the stationary, or the stationary distribution at those covariate values.
Sorry, I don't want to
I think it's a pretty minor point in fixing it, even when you have covariates. I've never seen it make a difference to anything, so I think it's pretty common to do. It's less parameters to estimate.
I have
But
another context. I'm sorry.
okay, so to actually find those parameter estimates, we use numerical optimizers. And so basically, if we consider that this is the probability density, so our likelihood function, you're going to start somewhere along this surface, and there's going to be some algorithm, you don't need to know the details of it, that moves around the likelihood, and eventually we want to get to this point, which is going to give us the most likely, or the best parameters. And the reason I'm bringing this up is that one thing that we have to do in our HMM is choose starting parameters for that, for those optimizers. And so basically, for each parameter, we need to choose what value to start at. And this is important because if we choose poorly, we can end up converging to something called a local maximum. So if we start here, actually I'm actually not sure where this was starting, but we might move up the gradient here and stop when we get to this point, because the algorithm is going to see, okay, we're going down now, so that must have been better. But actually what we wanted to get was here. So if we pick better starting values, we're more likely to get to a global maximum. And like I said, I'm bringing this up because the packages that we're using make you specify the starting parameters. So the package isn't going to guess them for you. You actually have to have that kind of first guess. One thing to note is that setting these starting parameters is not the same as fixing parameters. This is something that I often see people confused about, is they think that we're setting the starting parameters to a step mean of 10. That's not, you're not fixing the parameter to 10. It's just a starting point for the optimizer. And so, yeah.
But the model, as you fix, like, as you declare your beginning parameter, the model will create other starting points for other variance parameters from this starting one, and then deliver you the best starting.
Yeah, so basically numerical optimizers are going to use some algorithm to explore this likelihood. And so say for this parameter here, if you set the starting value to, I don't know, what is this, negative 2.5, that's where it's going to start. And it's going to try going up or down. I'm not totally sure exactly, depending on your algorithm. It's going to try going up. And if the likelihood is going up, it's going to keep going up that surface, because that means that it's more likely. And then eventually it's going to stop somewhere. Usually when it starts going down, then it kind of recognizes that it's reached the peak and now it's starting to go down, so it was more likely to be. Does that kind of make sense?
Yeah. But my question is,
Sorry.
if you define a not good starting value, so it probably won't reach the best likelihood.
I mean, it really depends. Depends what your likelihood looks like, which I guess you don't really know. Like, we don't look at our likelihood. If you have something that has kind of multiple modes like this, you can converge to a local maximum. So it's not actually the highest point, it's one high point. Whereas if you had a likelihood surface that was like only half of this, it doesn't matter where you start, it's always going to go up. So it depends what your likelihood actually looks like. Yeah?
Maybe it's a silly question, but what are the parameters? I know.
No. So the parameters are going to be the transition probabilities and the parameters, the observation parameters. So that's going to be the parameters of those state-dependent distributions. So like we had a gamma distribution of step length, so there's a mean parameter and a standard deviation parameter. That's what we're trying to estimate, and so you would need to set an initial value for each of those parameters.
So you look at the data and then you decide.
Yeah, so that's kind of the most common thing to do, and that's what I was going to show here. A really common way to do this is to look at your observation variables and kind of choose what you think might be reasonable values. So if you're trying to fit a two-state model and you have a step length distribution that looks like this, you might think that you have one state that has really short step lengths, and so maybe you set an initial parameter of close to 0, and then you might set one like at 2 or something. It's not an exact science, and a good idea is to actually try multiple starting values and kind of ensure that you're always getting the same results at the end.
So for this, you will fit all the time a new model with a new starting value, and
Yes.
that's it. Okay. Is there a faster way to do this? Because I guess for this you are always fitting one model and then another one with a new starting value, and then the third one, the fourth one, it's like 250, whatever. And it, to me, it feels like time consuming. So is there a way to just?
Yeah. So in one of the packages, we're in one of the packages that we're going to be using, there is an argument in the fitting function where you can specify to try multiple starting values, and it'll kind of automate it for you. I think it takes kind of random values kind of close to the starting values that you chose. But other than that, I think you would just have to manually fit a whole bunch of models. For simple HMMs, they're usually fairly fast to fit, if that helps. It's usually like, the order of a minute, not like days. One thing I was going to note is that for turning angles, it is more complicated to pick starting values, I think, because, for step length, you can kind of look and kind of guess where plausible means might be, and standard deviation is usually related to the mean. For turning angle, for the mean, it's probably reasonable to choose 0 for a lot of models, but the concentration is harder to interpret from this. Generally you might think that you have one state that has a low value and one that has a higher value, but I think from looking at the data, especially if you haven't looked at a lot of von Mises distributions to kind of understand what the concentration means, it's a little bit harder to choose, but there is a vignette online written by the author of Move HMN and Momentum that talks about this in a little more detail. By Theo Michel, he's the, yeah. You could probably just Google this name and it would come up. Okay. So assuming that we did all of that and it all went well, this is what our results would end up looking like. And so the first thing we might look at is the state-dependent distribution. So this is our observation model. And so it's an example where we have 2 states. And so you can kind of see here, again, this looks like very slow movement, so slightly faster movement. The slow movement has kind of more variability in the turning angles. And so this is really commonly what a 2-state model looks like. And like we kind of already talked about, this is a really important point to actually look at these and determine if they make sense and if there is a biological interpretation to these distributions. Okay. And so then for the state process, the parameters that we are estimating is the transition probability matrix. So just to refresh your memories, this is the probability of switching between each combination of behaviors. So that's one thing we would look at. There's typically pretty high values along the diagonal, which is the probability of staying in the same state. Oh, I guess one thing actually I should have mentioned is that we typically don't have to set initial parameters for the transition probabilities. Packages will usually do that, and I think it's because it's usually something kind of big along the diagonal. Other things that we're going to look at is state decoding. So this is going to be looking at kind of what is the most likely state for each observation. It's typically something that people are interested in knowing. And then calculating things like how much time is the animal spending in each state. So something like an activity budget. Okay. Does anybody have any questions? I need to drink, so. Okay. Okay. So one of the things that we're interested in is identifying the most likely state for each observation. And so one way to do this is using something called global decoding. It's using an algorithm called the Viterbi algorithm. And so sometimes we call them the Viterbi states or the Viterbi sequence. And so this is going to give you a predicted value for each observation. And so this is usually something that you're interested in looking at. Another option is to use local decoding. And so this is going to give you the probability of being in each state for each observation. So you're going to have as many probabilities as you have states. And so this is going to be some continuous measure from 0 to 1, not just either state 1 or state 2. It's going to give you the probability for each. So this is just showing the probability of one state over the time series.
The horizontal axis is the time.
Yeah.
Yeah.
And so usually there's pretty good agreement between local and global decoding, but there can be some variability. So this is showing an example where this is the Viterbi state. So these are all the estimated state 1s from the Viterbi sequence and state 2. And then these are the state probabilities. And so usually there's pretty good agreement between them, but the state probabilities does give you some indication of how much kind of uncertainty there is in that state classification. So like if everything was around here, it might not be great. I think it's probably a good idea to kind of look at both and see if they're generally agreeing. Okay. Yeah.
This is something that's a little bit complex for me, but how you pick the decoding? Like if you're using the Viterbi algorithm or the forwards and backwards algorithm. So you need to pick one of these, yeah?
So the Viterbi algorithm will give you the most likely state. So it'll give you like either a 1 or a 2 for each observation. And so that'll be using the Viterbi algorithm. Whereas local decoding will give you the probability of being in each state for each observation. And that's using the forward-backward algorithm. So you could do both. They'll give you different outputs. Yeah.
One question.
Yeah.
So in the figure of the state probabilities, when we are in the bluish, is that we are certain that we are in the state 2.
Yes, so this, yeah, you can only look at one at a time, right? Because it's the probability of each state. And so here, the probability, when it's dark blue, it means that the probability of state 2 is very high.
So when you are in between, there is like an uncertainty that you can be in both states at the same time, but
yeah, I guess it kind of indicates that that observation, it's less clear which state it's in if it's close to 50%.
okay,
Yeah. Yeah, another thing that people are often interested in is calculating some sort of activity budget, so how much time is spent in each state. One way to do that is to actually calculate directly from the transition probability. There's a transition probability matrix. You can directly calculate that. Another way is to just take the proportion in each state from the Viterbi sequence. Okay. I've been talking for way longer than it feels. Okay, so I'm going to talk a little bit about software, and then we'll finally get into some actual coding. There's quite a few different packages for HMMs in R, but there are a couple that we're going to be focusing on. So Move HMM and Momentum are packages that are specifically developed for HMMs for animal movement. And so Move HMM came first. It's a fairly small package. It doesn't have a ton of functionality. Momentum is a much larger package that has a lot more options. And the last one that I'm not sure that we'll have time to talk about is a package called HMM TMB, which is a general HMM package, but it's really flexible and quite fast. Okay, so I kind of already talked about this. They just kind of mainly vary in the different types of things that we can do. And later we'll talk about covariates. Multiple imputation you can only do in Momentum. And then HMM TMB can do stuff like random effects and splines. So many slides on which package to use. I've kind of already covered this. I guess one thing that I wanted to note is that it is partly going to come down to personal preference. For example, you can combine them too, so I would probably use Move HMM or Momentum for data processing, and then HMM TMB for analysis, for example. Unless you need something like multiple imputation, then you would probably have to use multiple imputation or Momentum, unless you want to do that all manually. And I just wanted to note, all of these packages have really good documentation online, so there's tons of vignettes on the GitHubs or on the CRAN, sorry, for each package. Okay, so this is kind of what we're going to talk about. We're going to talk about preparing your data, choosing your model formulation, fitting, visualizing your outputs. In the first tutorial, we're not going to talk about covariates or diagnostics. We can talk about that a little bit later. Okay, so that's going to bring us to the first tutorial where we're just going to cover fitting some basic HMMs. And the data that we're going to be using is Argos locations at, it's a little bit of a funny resolution, a 9.6 hour resolution from 15 elephant seals. This is from a paper by Michelot et al. From 2017. And we're not going to actually cover all of this data preparation, but the data was regularized using a state space model. And so we're actually assuming that the locations have no error, even though they are imputed locations. Just for simplicity, we're not going to take that into account. Okay. Does anyone have any questions? You guys can all read that, right? I'm joking.
Still basic. The code is still basic.
Still basic, yeah. So this is the first script, number 1.
I think we need to adjust font size
Do you know how?
Yes.
Okay. View.
Tools.
Tools.
And then mobile options. And then appearance, maybe? Try appearance. Oh, sorry, from somewhere else. And then yes.
Do you know what?
Just zoom.
I mean, zooming will zoom like the whole.
No, I think we'll make the text bigger.
They'll just make the text bigger? I mean, it makes everything bigger.
But then if you close the web options, I think now at least they can follow where you are on the. So.
Yeah. I think you were suggesting to just change the font size, which wouldn't change like the window size, right? Sorry, just let me play with this for a second. Oh my God, where's the bottom of this? There we go. Yeah, because then everything else isn't huge. It's just the code that's big. Oh my God, I can't drag this. Is that big enough? I could make it bigger if people at the back still can't see it.
Yes.
Okay. Can I only go from 18 to 24? Is there nowhere to type it in?
Oh, yeah, that's good.
You have no space to type.
Okay, let me see this for a sec. This is readable for everyone, yeah?
Can you put the team in white in the art? I think it's a little bit it's not that simple.
You want it in white? Sure.
Because the letters some are green and with the black.
Oh, is it hard to see on the screen? Okay.
I think you can do it. I think it's
What is it? It's hard for me to know which ones look. Does that one look okay? Good? Okay. Okay. So I kind of already explained what the data is. These are the columns that we have. So there's a column for ID, for the X and Y coordinates. They're called X and Y, but these are latitude, longitude. Distance is a covariate. We're not going to use it right away, but it's the distance to that to the colony that I showed on the map. I don't know if you saw that. And then there's the time of the observation, the day of year that the observation was recorded, and the time of day, which is TOD. And I was pulling up a summary just to show that there's no missing observations, there's no NAs or anything like that in our data.
The distance units kilometers.
Yes, I believe so. I believe it's kilometers. Yeah. It's definitely not meters. Okay, so I already showed this data, but this is what the data looks like. It's colored by individual. The black square is the colony. Okay, so the first thing that we're going to do is prepare the data for the HMM. And so in this data, there's no step lengths or turning angles, which are going to be our observation variables. And so I guess up until now, you've used other packages for calculating these variables. You could also use those packages. You don't have to use the functions in Momentum or Move HMM as long as you have data that has all of the observation variables that you want. But prep data is a function in Move HMM and Momentum that calculates these metrics for you. And so you input your data, and then this type argument is to specify whether or not your data is projected. If it's projected, you would type UTM, or whether it's latitude, longitude, which is LL. And actually, one thing to note is it's a good idea to input this because Move HMM and Momentum have different defaults. So if you don't put it, I think Move HMM assumes latitude, longitude, and Momentum assumes projected. So I think it's a good idea just to put it in so it's clear. I've had problems where you have both packages loaded, and then I can't remember which package it'll use, maybe the most recent one that you loaded. I'm not sure what the default would be. Anyway, it's a good idea to just specify it. Okay, so that will calculate the step length and turning angles. And so then the output of that is going to be this momentum data object. where if you press summary on it, it'll give you the different IDs, the number of observations, and then the step length and turning angle summaries. And so you can see that for step length, we do now have some missing observations because we need 2 locations to get a step. One of them is going to be on A. And then for turning angles, we have even more missing observations because you need 2 steps to get the turning angle. And so it's just to show you here that the angle is NA at the beginning, and there's also an angle missing at the end of the time series. Okay. So awkward.
And
Oh, this isn't working. Sorry.
maybe this package thinking of this guide so that the name is at the end.
Yep.
Nice. So for the step length, we get
So the step
one
length
NA at
is,
the end. And then for turning angle, we have 2 NA.
this is something that I always have to think about. Like, it always takes me quite a while. Well, the turning angle has there's also a NA step. Oops. Oh, never mind. Yeah, no, you're right. There's a turning angle missing at the beginning, but step is missing at the end. Yeah, that's right.
No, I'm
Yeah.
right?
Okay, so this is just looking at the distribution of the step length that we just calculated, and same for turning angle. And so you can actually see in the step length distribution, it's potentially actually a nice one for an HMM because you can actually almost see that there's bimodality in the distribution. So it looks like there's some observations that have kind of these shorter step lengths and kind of a second mode a little bit later. Which that is pretty uncommon. Usually it just looks like that kind of like exponential decay. Okay, and so one of the important decisions that we have to make is choosing the distributions for observation variables. And so for simplicity, I'm just gonna use a gamma distribution for step lengths and a von Mises distribution for turning angles. And so for momentum, this is how you input it. You have to input it as a list where each element of the list is a distribution name for each observation variable that you have. So we just have step length and turning angle. And so that's what it ends up looking like.
And one person, where are we saying that the step length will have a gamma and the angle will have, and turning angle will have the gamma distribution?
Yeah, with drinks and stuff, they can come in, right?
I don't know what all times.
That's fine.
Could it be like?
It could be different.
Yeah.
Yeah. Yeah, so this is kind of what we were talking about, choosing those state-dependent distributions. You could try different ones and compare them if you wanted to. I'm not going to do that in the tutorial. For simplicity, I'm just going to use gamma and von Mises, but yeah, you could definitely try different distributions. And so these names that we're specifying, you can't just write von Mises. It has to follow the naming convention of R, or of the package. And so if you look at the vignettes, I think they have lists of the different distributions that it supports and what the names would be. Okay, so the first thing that we're going to do is fit a two-state model with these distributions. And so, like I mentioned, we need to choose initial parameters. And so these initial parameters I chose just from looking at the data. So I chose the first one to be a mean of 10 and the second one to have a mean of 30 because it kind of looks like the two modes that we're seeing there. And then I was going to say, I usually set the standard deviation to kind of like half the mean, but here I did not. I set that to the same as the mean, but usually the standard deviation is going to be related to the mean. Like you wouldn't expect to have a standard deviation of like 50 if your step lengths don't have that range. And then, sorry.
Could be pregnant with 2 times 10, 30 centimeters.
Yeah, so this is actually one thing that I'm not super wild about with momentum. How you have to specify the initial parameters is, so we have a two-state model, and so for the step length distributions, we're going to have 4 parameters. There's 2 parameters for the distribution, and there's 2 states. And so this is, you have to input it in the correct order. It has to be the mean of the first state, the mean of the second state, the standard deviation of the first state, the standard deviation of the second state. And so with 2 states, it's not too bad, but when you start to get into many states, it starts to get a little bit confusing. You have to like really track that you're inputting it correctly. And for the angles, I'm choosing initial parameters around 0 for the means, and then something with a really low persistence and something with slightly higher.
But the parameters, you choose these parameters looking the graphics.
From looking at the distributions of step lengths and turning angles. Yeah.
Why do you put 2 times 0 for the angle?
Because it's the mean turning angle, so it's really common for, even when you have 2 states, for both of them to have a mean at 0, which would indicate that they do have some level of directional persistence. So that's usually really common to have means of 0. Does that make sense?
Yeah, but both states the mean is 0 and the standard deviation is different. So one they really go.
Yeah, so, I mean, so first of all, just to be clear, these are the initial parameters. We're not fixing these parameters or anything. But often what we see is to have 2 states both with means at 0, but that vary in their concentration. So they might both have 0, which would indicate that they tend to go the same direction that they were, so there is persistence. But if there's very high concentration, it means that like there's a lot of directional persistence. It's more likely to be like close to 0. Whereas if it has low concentration, it's more spread out. There's more variability in the direction that they go. Does that make sense?
Yeah. Maybe one question.
Yeah.
In the line 50,
Yeah.
it's written mean 1, mean 2, standard deviation 1, standard deviation 2. But in line 52, there is like 10, 30, 10, 30. Would you then say that it should be 30, 30, 10, 10 instead?
No, it's because it would be
Or is just
this would be the mean of the first state, so it's 10, so it's smaller than the mean of the second state, which is higher, it's 30, and then the standard deviation of the first state, which would tend to be lower if you have a slower mean, and then the standard deviation of the second state, which would tend to be bigger because it's a faster moving state. So HMM-TMB, I think, actually has a much nicer way to input this, where you specify that it's like the mean and then you do your list of means. Anyway, it's a little bit easier to track. Okay, so that was just setting the initial parameter. So that's just where the optimizer is going to start for each parameter. So then we can actually fit the model. I'm going to start running it. So here we're specifying the number of states. We have a 2-state model. These are the distributions that I set a little bit higher. You could also do this like in the fitting function if you wanted to, but I like to specify it first. Par naught is the initial parameters, which is given by this. And one thing that's a little bit, I don't know if it's controversial, but in momentum, by default, it actually doesn't estimate the turning angle means. It assumes that they're 0 and it actually fixes them to 0, so it doesn't estimate those parameters. You can do this if you want. I personally like to estimate the mean. And so to do that, you have to actually set manually that you want to estimate the mean of the angle. And then this retry fits function I mentioned before, it's going to try more than one set of initial parameters. And I could look into it again. I can't remember exactly how it does it, but I think it takes some kind of random perturbations around the initial parameters that you started. But I can't quite remember the details. Okay. So if you just print the model, it gives you this long list of all of the different parameters. So we have the step parameters, angle parameters, etc. I'm going to go through each of them in a little bit more detail. So these are the observation parameters for the step length distribution. And so these are the estimated means. So 9 kilometers in the first state, 34 in the second state. So that is kind of a slower and a faster state. And then these are the estimated standard deviations of the gamma distribution in both states. Sorry, I'm still doing the thing where I go down low at the end. I think it's because I feel like I'm yelling, so I'm like, okay.
But you just said that for the fault, the turning angle is 0 with this package. If you don't specify your parameter for the turning angle.
So if you don't set, if you don't use this argument of the fitting function, by default it will fix the turning angle means to 0 in both states. So if you want to estimate the mean of the turning angle distribution, you have to set this where angle equals true in here. And then if you did that, you wouldn't set these initial parameters. So you would only set initial parameters for the concentration parameters.
But in that case, that it's 0 also, it doesn't matter. Or yes?
What do you mean?
That you said that for the fault, it's the estimation, it doesn't estimate.
So yeah, by default, momentum won't estimate your turning angle means. It'll just fix them to 0, so it assumes that they're 0. And so then you wouldn't have to set these initial parameters because you're not estimating anything. So you would only have 2 initial parameters to set for the angle distribution. Yeah, and then so these are the estimated angle parameters. So, I mean, as you expect, the means are close to 0. And then in state 1, we have a lower concentration, so that was the slower state. So that's kind of what we typically expect, to have a slow, non-directed state. And then the concentration in the second state is much higher. And so then we can also plot the state-dependent distributions. I'm setting, if you don't set plot tracks equals false, it'll plot the Viterbi sequence of every track segment or individual. So this is the angle distribution. So as we kind of talked about, they're both centered on 0, but state 1 has a lot more variability. So that's the orange state. So it's a lot more directionally variable. And the blue state has a lot more concentration around the mean of 0. So this is a little bit awkward how I have to do this. And this is the state-dependent distributions for step lengths. So again, kind of the slower state in the orange and faster in the blue. Do the state-dependent distributions make sense? Does the results kind of make sense? Okay, so that was the observation process of the model. For the state process, if you just look at, this is a little bit of a technical point, but this is actually the parameters if you just like look at the MLE. These aren't actually the transition probabilities, there's like a transformation of them. Well, it's actually what's estimated, but we can transform them into the transition probabilities. It's a little bit of a technical point, you don't really need to understand it, but just if you're wondering why these parameters here aren't transition probabilities, it's because they're on like a different scale, they're transformed.
One question.
Yeah.
How did you run the plot with the step, the one that you're showing up there? How did you run it? Or is it they come together?
They come together. It's actually one thing that I find is a little bit awkward to use with momentum sometimes is when you use the plot function, it plots everything at once, and there's this ask argument where if it's true, you hit enter and each plot will come up sequentially. But yeah, so when you run this plot, it'll give you all of the model plots. Okay, but if we pull a gamma, this is actually the transition probability matrix. And so you can see that if you remember the transition probability matrix, the diagonals are the probabilities of staying in the states, and the off diagonals are the probability of switching between different states. And so here, these numbers basically indicate a really high degree of state persistence. So when they're in state 1, they're really, really likely to stay in state 1. Yeah. And so then from the transition probability matrix, we could calculate the stationary distribution, which will give a rough estimate of how much time they're likely to spend in each state. And so here it's saying about 62% in state 1, 37 in state 2. And another way to do that is to use the time and states function, which I think just calculates the proportion of the Viterbi sequence in each state. And in this case, we have a really high degree of agreement between these two, which is, I think, typically what you would expect. Yeah.
Would you be able to do this, splitting it across different biological and relevant time? Like, it would be interesting to know, for example, if in a specific season they spend more time in state 1 than in state 2. Then would you put that as a variant, or how would you be able to get those separation of the state across, let's say, season, or what you were saying yesterday, migration, breeding, relevant moving on?
Yeah, that's a good question. So yeah, one of the really common things to do is put covariates on the transition probabilities. So you can look at how a covariate affects the probability of switching into a particular state. We will cover that later. That's a really common thing to do. And so it's kind of like getting at the drivers of behaviors. Yes. Right now we're sticking to covariate-free models, though, just for simplicity. Yeah. Okay, and another thing that I talked about is state decoding. So we can use the plot function. This is just for a given animal. This is the most likely state for each observation. And so you can kind of see from this, the orange, can't remember which number that is, state 1, tends to be kind of these shorter movements. So you can kind of see the different behaviors. You can also run the Viterbi function to calculate it for all of your data. And so, as I mentioned before, it'll give you a single number for each row of your data. And the other option is to calculate the state probabilities, which will give you for each observation, it'll give you as many probabilities as you have states. So this is just kind of contrast the difference between those outputs, where Viterbi is just one number, whereas this will give you multiple numbers and state probabilities. I already did this. Here I'm just saving it to the data because I want to make a plot. I don't actually think I included cowplot in the list of packages that need to be installed. You could just, if you want to look at this, you could get rid of the plot grid and just plot each separately. But I just wanted to show this top plot is the Viterbi sequence, so this is most likely state. And then this one here is the probability of the second state. So it's probability of the fast state for each observation. And so typically I think what you would want to see is that these look quite similar, which in this case they do. Yeah.
It's choosing just one state. Like, what if the probabilities are quite close? I think it's uncertain which state that location.
Yeah, I mean, that would probably indicate that there's like quite a bit of overlap between your states. If there's, like if you picture your state-dependent distributions, if there's a lot of overlap in those lines, and there's probably going to be quite a bit of state uncertainty for each observation because of that overlap. Whereas if you have kind of these really nice separable states, usually you end up with state probabilities that are close to 1 or 0. Does that kind of answer your question?
Yeah, do you do anything if there's like only a couple like points that are have close probabilities? Do you filter them out? Like, how do you do it?
No, it's just, I don't know, I mean, like, if you looked at your state probabilities and everything was like really uncertain, maybe it means that, like, I mean, I don't know, I don't have any super concrete thoughts here, but to me, my first instinct would be is that there's a lot of overlap in your states, and maybe you have too many states or something, and everything's really uncertain. But no, I mean, it's fine for some of your observations to have state probabilities close to 50. There's always going to be some states that kind of reasonably could come from either observations that could reasonably come from either state. Does that make sense? Okay. So that was a two-state model. We're going to also fit a three-state model and kind of compare the results a little bit. So now you have to set initial parameters, but you need 3 means, 3 standard deviations for your steps, 3 means, and 3 concentrations. So you can kind of see that it starts to get a little bit, you need to like make sure that you're doing them in the correct order. So it's mean, standard deviation. And again, these are just your initial parameters, so you're not actually fixing anything. And again, I just did this by kind of looking at the data. And I guess I'm assuming that it's probably going to capture a really slow state, an intermediate, kind of slightly more persistent, directionally persistent state, and then a faster, even more persistent state. And so then this is just the same code, but with 3 states instead of 2. Does anyone have any questions while I'm waiting for it to fit? I should always remember to start fitting it while I'm still talking.
All of it would take with a huge amount of data. With a huge amount of data you can take today.
I mean, it really depends what you mean by a huge amount of data. Usually, even with like, I mean, so it really depends on how many observations you have. Usually for movement data sets, it's not more than like a few minutes. But it depends on the complexity of your model. It depends like how many states you're fitting, if you have covariate effects, how much data. It's usually pretty fast though.
So the first goes back on to specify distributions. Can the distributions is just
oh yeah.
Can you for the different states can you specify distributions?
No. As far as I know, no.
No, because you can't compare the likelihoods. They have you can't mix the distributions. Because they will have different number of parameters.
Yeah, sorry, I didn't mention, but I'm using the same distributions as we did the last time, so that's why I'm not re-specifying them here. I'm still using gamma and von Mises. Okay, so I mean, I'm just going to go through these fairly quickly because we already went through this in quite a bit of detail, but kind of as we expect, there's kind of a slower, intermediate, and faster state. One thing that is worth mentioning here, though, is when we have the 3-state model, these are our turning angle parameters. And so actually for state 1, we don't have a mean of 0 anymore. It's actually a mean close to pi, which indicates directional reversion. And so it's less common in a 2-state model, but it's actually, I think, relatively common when you get into more states. And I think it's likely because when you have an animal that's very stationary, I think there's commonly like an artifact of the data where if there's a little bit of measurement error, even in GPS data, and so if they're just sitting there, it still looks like they're kind of bouncing around, and so there's often kind of, I think usually it's kind of an artifact of the data, but often we do get a mean in a really slow state close to pi. And so, I don't know, maybe that's kind of whether or not you want to estimate that, it's biologically maybe not actually relevant, but it is capturing something in the data. I just thought that was worth pointing out. If we had not estimated the mean, everything would have been estimated to be 0.
Why is this more specific of a 3-state and not the 2-state? Listing of the arrow. And wouldn't you see that in the 2-state, in the slower state, let's say, in the stationary?
Yeah, my guess is that when you have 2 states, the slow state is going to capture more of the longer step lengths, whereas when you have more clusters, the slow state is going to be like even slower. And so it's not going to, and so I think when you have 2 states, usually overall it still ends up averaging to a mean of 0 or something that has some level of directional persistence. That's my best guess anyway. And so yeah, so this would be what the angle distributions look like. And so you can actually see that the density here is actually closer to the tail, so that's the mean of pi. And then I guess there's also a step length. So yeah, these are the step length distributions. So yeah, very slow state, kind of this intermediate state, and then a faster state. And you can kind of see that as we get into more states, there's more overlap between those states. Okay, just looking at transition probabilities, again, pretty high along the diagonal. And then we can also calculate the kind of time in each state, or some sense of the activity budgets. And so this is just showing the Viterbi sequence of the 3-state model compared to the 2. And so you can kind of see that this intermediate state is kind of, yeah, that's the intermediate state. It's kind of capturing some of these segments that previously were being categorized as kind of that faster state. Huh?
So I have a question in my son, but is longer step length always associated to smaller turning angles? Like why, like, right? Because
Yeah, I am thinking about physically, yes, without turn across.
so that's why we always expect like these curves. They will always these curves that you showed us the distribution for the step and for the turning angle. They will always be gradual in the same direction. Like these 3 states, could they ever combine differently? I'm just thinking there's only one way that turning angle and step length can be combined in different states. Let's say we have whether it's 2 or 6. I'm just thinking if you always go in the same direction. The direction now I'm not meaning the direction.
Yeah. I wouldn't say that you could never end up with something that diverges from this. This is just kind of the most common, and I think it usually makes sense from a biological perspective that when animals traveling fast, they're often going somewhere. They're traveling to get somewhere, versus when they're maybe looking for food, they're kind of moving all over the place. Versus when they're resting, they're really. There's probably, I don't know, it depends on your species. Like there could be situations where you end up with something different that still makes sense.
But can I just, you have 2 parameters, speed and turning angle. And there is just so much you can extract from 2-dimensional data. So if you had more variables, you could maybe also find more states, which are more combinations of those 2 variables.
Yeah.
Essentially, if you have 2 dimensions, and 2 dimensions you can split maybe in 4 sections. High, low, low, high. So, and that is pretty much it. So, in that sense, yes, eventually you need to have more information in order to extract more states. Because, yeah, I mean, you can split speed in 3 sections, but speed and turning angle are not independent of each other. Not in physical systems. You cannot go fast and random in all directions. Just morphologically, physiologically, it's not possible. You run and then try to run fast around the court. You will have to speed, to take out speed in order to be able to take the momentum. So this way.
That's why it was saying my.
No, it's not stupid. It's something that you have to think about.
Yeah.
So how much will I extract from a limited amount of information? Because your variables are information. Now you are limited in information to 2 dimensions. So there's a finality to how much you can extract from 2 dimensions of information.
I mean, yeah, we kind of talked about that a little bit earlier, where we looked at the example of including dive data as well, where if you have 2 behaviors that have similar movement speeds, you could differentiate them based on where they are in the water column, for example.
So, in case you want to add another parameter at altitude or that, you include as a variable for understanding how this impacts the state, or you include this also as the step length and turning angles here.
Yeah, so if you think it's a variable that helps to characterize the state, like I was talking about with depth, whether or not they're deep or at the surface is a different behavior maybe, then you would include it as you would step lengths and turning angles. So you would, you would define a distribution for it up here. You would set initial parameters, you would do all of the same stuff, and then you would have, instead of just having state-dependent distributions for step lengths and turning angles, you would have another set of state-dependent distributions for say, dive or altitude, whatever, or depth or altitude.
You're like, I don't know, 1.5 hours. We should talk. You want to make a break?
I mean, I think we're in like actually, I think that was the last line of code, so yes.
Before, when we were running the article, we were like after the two-state model, like with the fit HMM function, there are observation parameters and state process parameters.
Mm-hmm.
We were having doubts on the differences.
The difference between the observation parameters and the state process? Here, maybe, I'm not sure if it'll help going back in the slides, but we can try. So these, I mean, I kind of talked about there's these 2 kind of separate parts of the model, and the state process describes how the animal switches between states. So that's why the transition probabilities are the parameters of interest, because they describe those state switches. Whereas the observation parameters describe how the states give rise to the data, and that's through those state-dependent distributions. And so they're the parameters of these probability distributions that describe the step lengths and turning angles in each state. Am I just repeating the same thing and it's still not? Okay.
But our question was like, okay, you both are outputs from the model, but
yep.
You use the observation like a validation or something like this, and the other is to estimate the probability of changing the state.
Sorry, could you repeat that? The state process is the probabilities of switching between states, yes.
For what do you use the observation parameters? Like to check, like to validate or to check if this model that you have performed of your states is like kind of approaching some kind of your data? Or...
Yeah, so you want... Go to the R code? Yeah, sure.
And then where you are looking at the output, hit it on
Not the same. Okay.
Yes, there.
So, sorry, what's the question?
So, run this, and then you actually went, so state 1, state 2. I think they can't distinguish between the transition probability of the discrete states, being in state 1 or being in state 2, and then the actual estimates of the parameters of the behavior or speed and turning angle within state 1 versus within state 2. You know, the mean and standard deviation.
So the observation parameters kind of define what the states are, right? Like you have fast movement versus slow movement, and that's being captured by the state-dependent distributions. And so then, kind of, given those state-dependent distributions, there's going to be some probability of switching between the states. Sorry, I think I'm not 100% sure exactly what the confusion is, which is why I'm struggling to answer.
Maybe
you can.
Sorry.
No, go ahead.
So remember that there are these two. So we say there are two states. Okay, both of them are gamma distributions, and we assume one is like this, the other one is more like something like this. Okay, so these are our two. We are saying there must be two gamma distributions. We define that. We don't derive that from the data. We say there are two states.
Yeah.
Now this is just for step length or speed, because we have regular sampling. Step length equals speed. Now the task here is for the optimizer, and each of these distributions is defined by a mu2 and I don't know mu1 and a spread value which they have. Okay.
Yeah.
And so the task to the computer or the optimizer is, I know there are two gamma distributions. Find me the two gamma distributions and tell me what mean and standard deviation each of these twos have. Okay? So this is what that says. In addition, it's a hidden Markov model. In addition, we're saying there is a probability of the animal switching between this and that. And there is a probability that the animal will switch from a state being in state 1 to flipping into state 2. This probability, the computer also estimates. What is the probability of the animal being in state 1 to switch into state 2? And that is then here.
No, those are the observation. Be the gamma.
Yeah. Is that the confusion you have? So there is, I am in state 1, and there is, as also Natasha said, with time, the probability of me changing into state 2 grows. But most of the time, I'm in state 1 and I'm going to stay in state 1. Meaning, I'm following this distribution. So my observations of step length, my observations of turning angle belong to this distribution. It's more likely that they belong to this distribution. There's always a chance that I behave similar to state 2. So therefore, it's not like you're in state 1 100%.
Yeah.
It just says, if I look at you right now, I would say probably state 1.
Yeah. More probable one state than the other.
Exactly. And there are like these diagnostic plots where you look at the probability of state 1 and the distribution where you find the points of being in state 1 or state 2. And then what you also can look at the probability of being in state 2. And sometimes the HMM cannot figure out, it's like, I don't know, I mean, it could be either.
Yeah.
Is that?
It's the same in different. Sorry.
Yeah.
No, that was helpful. Thank you. Are you familiar with like mixture models more generally? Because you can think about this as kind of like a mixture model with a level of temporal dependence. So this is, if you ignore temporal dependence, you would just have a histogram or like a whole bunch of data, and you would just cluster it without taking into account the structure of time. And with the HMM through the state process, you're also acknowledging that what state it's in depends on what state it was previously, and so that's going to affect. It's kind of taking into account that you're not likely to just constantly be bouncing between states. So the clustering will be slightly different. Yeah.
But in that case, observation is like fitting the model to adjust that this is that state and this is the other state, and what we want is the probability of change between the states. Like the observation is like for fitting the model, for indicating that this is x value is this state, x values are that's one state, and another values and add another state?
So you would, during model fitting, you're estimating both the transitions between states and the observation parameters, so what those states look like. So it's happening together. So it's not like you're just clustering and then estimating transition probabilities. Everything's being estimated together in kind of like that dependent mixture model. That's why I was calling it a doubly stochastic model, because there's kind of these two probabilistic elements that need to be estimated. Yeah.
One quick question about the package itself. What is the difference that returns for me from a stationary from the model and the function is stationary and the function timing states? Because it's basically the values are pretty the same. But I understood that timing states is how long is how much time each signal is in the state. But what is the difference by stationary?
Yeah, so stationary is going to calculate, so when you don't have covariates on the transition probabilities, which we're going to talk about, you can calculate the stationary distribution of the Markov chain, which I think is basically assuming that if time goes to infinity, so you have like an infinitely long time series, what proportion of that time series would be in each state, kind of given those transition probabilities. So it's like a mathematical thing. You can calculate it directly from the transition probability matrix. Whereas time and states, that function, I believe how it works is it estimates the Viterbi sequence for your actual data, and then takes the proportion of time or proportion of observations that are in each state. Yeah. And so time and states, we're going to talk about it, but is useful when you have covariates on your transition probabilities and you can't get that stationary distribution anymore, because it's not stationary, it's evolving with covariates. But yeah, that's the difference in this case. Okay. And I guess one thing that I didn't really talk about in the tutorial is kind of assessing whether or not those states made sense biologically and whether the 2-state or 3-state model is better. And that's largely because I'm not a seal biologist. And I think it's really going to come down to, you as the biologist looking at it and kind of judging whether or not you think those make sense as states of your species and your animal. My guess is that the 3-state model was better for the seals. It seemed reasonable, and I think actually in the next tutorial we're going to look at diagnostics a little bit, and I'll show you a couple things to look for. But we do still have like over a week and a half, so hopefully some of the stuff we can keep going over, and yeah. I realize this is like a lot all at once, so. Okay. This maybe seems like an obvious slide, but what are covariates? Basically, they're things that we think are going to affect the animal's behavior or their movement. So it could be things like temporal factors, time of day of year, something to do with the animal's state, like their body condition, or something to do with the animal, like their age or sex or something like that, or environmental drivers like resource density. The reason I'm talking about this is it's important to note that the step lengths and turning angles are not covariates. They're the observation variables or the data streams. And so that's not what I mean when I'm talking about covariates. They're something that's going to affect either the observation process or the state process, but they're not the observation variables. Okay, so probably the most common form of covariates to put in are covariates on the transition probabilities, so in the state process. And so this would answer something like, does a given covariate affect the probability that the animal switches into or is engaged in a particular behavior? And so usually we kind of think about this as being useful to understand the drivers of animal behavior. Okay, so just a reminder, this would be our transition probability matrix. These are actually the parameters that we're estimating, so that's why I'm writing it like this and not just to emphasize that we're only estimating 2 parameters for a 2-state model. And so then we can specify For these transition probabilities, we can specify that they are some function of any number of covariates. So like, does the probability of switching from state 1 to 2 depend on a particular environmental resource, for example? Sorry, this is a lot on one slide. You notice that I had a logit link here, and that's to ensure that the probabilities are between 0 and 1. We can extend this to more than 2 states with a multinomial logit link. And this isn't super important that you understand this whole matrix, but basically we don't actually measure transition probabilities directly, but we have these covariates for the intercepts and then all of the coefficients, sorry, I'm not sure what I said. We estimate the coefficients, not the transition probabilities themselves, and then we transform those into the transition probabilities.
Sorry, can you say that part again? What's the matrix there?
Yeah, so we don't estimate gamma, which are the transition probabilities themselves. We estimate these coefficients, which is the intercept, and then the coefficient for all of our covariates. So if you think about this, we don't estimate this parameter directly, we estimate all of these coefficients, and then we can transform those to get a transition probability matrix. Yeah.
So you mean that the covariates influence the transition probability?
Yeah, exactly. Hearing a bird or something. Okay, so this would be an example of what this looks like. So say this is for slope, like the elevation slope. This is how that covariate influences the transition probabilities. So the transition probability for staying in state 1 or switching from 1 to 2. So this would indicate that kind of at these intermediate slope ranges, they're more likely to transition from state 1 to state 2. And then I guess similarly, they're less likely to transition from state 2 to state 1. Does that kind of make sense? I guess one thing to note here is that the Markov chain is no longer stationary. We can't get that stationary distribution that we were just talking about. So now we would end up, we don't just get a single transition probability matrix. We get a transition probability matrix for each time step that's dependent on the covariates at that time step. And so one way that we really often look at this that I think is a little bit more intuitive than looking at these is by looking at the stationary state probabilities. And so basically, these assume that if the animal was at these covariate conditions for an infinitely long time, what would the probability of it being in each state be? So it gives you something kind of like a stationary distribution, but for a given covariate value. And so it's kind of a way to summarize transition probabilities. And so you can see that this is time of day. It's more likely to be in state 1 at kind of these times of day, and then it's more likely to be in state 2 kind of later in the day. So I think these are kind of a pretty intuitive way to interpret the covariate effects.
The stationary here doesn't mean not moving, it just means staying in the same covariate space.
Yeah, it's not like the animal is stationary. It's if you assume that the covariate was stationary. Okay, are there any questions? I'm going to move on to the observation process, so if there's any questions about the state. So I think these are definitely the most common covariates that people use are on the transition probabilities, because people are really often interested in what kind of drives animal behavior, or how can we explain the patterns of animal behavior. But we can also put covariates on any of our observation parameters. And so the observation parameters, again, would be the step mean, the step standard deviation, the turning angle mean, and its concentration. So any of those parameters can be specified with a covariate. That's a function of covariates. And so this will answer if a covariate influences an animal's movement within a behavioral state. So it kind of models variability within a state. And I guess I kind of already explained this, but So if we have a gamma distribution of step lengths, this would be the state-dependent distribution where we have mu j and sigma j. Then we could take, say we want to model the mean step length, we can model it as a function of any number of covariates so within the state, the movement speed can vary. And so this is just a short example where the mean step length is modeled as a function of distance to colony. So this is kind of saying that okay, let me think about this for a sec. If state 1 is slow, that slow movement is slightly faster as they get further away from the colony. And so you can see that the step mean for state 1 is quite a bit lower. So so this is still, sorry, let me think about how to say this. These steps are always quite a bit shorter than the steps in state 2. One thing that can become a little bit of a problem, and I wanted to put an example here, but I forgot, is if you have a lot of kind of overlap between the states and then you're modeling them with the observation parameters with covariates, it starts to get really hard to interpret, is it like which state it actually is. You're allowing a lot of flexibility in those observation parameters that can get really difficult to interpret. So, I mean, you could think about if this was lower, so if it was closer to this range, there'd be kind of a range where they overlap. So it gets a little bit difficult to interpret observation parameters. I think one case that it could make some sense is to have like an observation variable for maybe the sex of the animal or something. You think that males and females engage in the same behaviors, but that maybe females move a little bit slower, and so you want to model something like that. Stuff like this I think can get really hard to interpret really fast, but it is possible. Okay, any questions about that stuff? Well, we have a tutorial to go over it, so I'm sure some questions will come up. Okay, so I'm just going to cover a few more HMM assumptions. Some of these you maybe don't need to know like kind of all the technical details of, but I just kind of want to make you aware of them. And some of them are going to come up during model checking. So one assumption that we have is something called conditional independence. And so basically, we assume that the observations are independent, conditional on the state. So we're kind of saying that, you know, state 1 comes from this gamma distribution, but it's just like a completely random draw from that distribution. So there's no correlation between the observations within a state. Although they're clustered together, so they look kind of similar, within the state there's no temporal autocorrelation. Another is that observation variables are independent from each other within a state. So you wouldn't expect correlation between your step length and your turning angle within a state, which also, both of these are often not actually true. Often we do have autocorrelation within the state, and a slightly faster step length within a state might actually be associated with turning angle closer to 0. So more directional persistence even within a state. And so something that you might see, and we're going to talk about this a little bit, is autocorrelation. This would be within a state, so we still have a lot of autocorrelation, but we will talk about that a little bit more. And we're not going to cover these in detail, most of these. Some potential solutions for this. First of all, covariate-dependent observation parameters, because that the autocorrelation would be kind of once you account for all of the covariates, is there still autocorrelation left? Another is to have an autoregressive HMM, and so that's basically where we add an additional dependence where now the observation at time t is also dependent on the observation before it. And you can actually do that by including a legged version of the observation variable as an observation covariate. So you could have like the mean step length depends on the legged step length. But we're not actually covering that in detail, but it's actually not that hard to do. And I think there's also methods to actually model that dependence between step lengths and turning angles within a state, but we're also not going to talk about that. But this is an assumption of an HMM that's we really often violate. Another assumption that we make is that our state process is a first order Markov chain, and so that's just saying that the state at time t only depends on the state before it. It doesn't depend on the state 2 times before it. It doesn't depend on the state 3 times before it. That's also often not really true. It is possible to specify a higher order Markov chain where there's dependence between multiple kind of levels. We're not going to cover that, but covariates and the transition probabilities can also help with this. So I presented those not because we're going to talk about them in a lot of detail. I just wanted to kind of like make you aware of some of the assumptions that we are making in the HMMs that we're talking about, and just kind of some potential solutions, and covariates can help with some of them. Okay. Any questions before I move on to model checking? Okay. So model checking, some of the tools we use aren't that different from other linear models. We calculate something called pseudo-residuals, which are analogous to residuals in linear models. And they measure how extreme observations are given the HMM that we have. So just like residuals in other models, we expect that they should be independent and normally distributed if all of the assumptions of our model is met. One thing is that turning angle residuals are a little bit weird. They're a little bit arbitrary because it's a circular distribution, so it's wrapped. How extreme, like you can think about a normal distribution and things really far on the tails are really extreme, but if you have something that matches here, extreme relative to what? It's a little bit of a harder pseudo-residual to calculate, and so I think momentum and move HMM assume it's like extreme relative to 0, whereas HMM TMB actually just doesn't calculate pseudo-residuals for the von Mises distribution. Okay. So we can look at the normality of our pseudo-residuals. So you can look at, kind of the histogram of our residuals and QQ plots, quantile plots, where basically we want that histogram to look like a Gaussian distribution or a bell curve, and we want the points along the QQ plot we want it to match this kind of one-to-one line. Probably most people are somewhat familiar with these model diagnostics. It's not that different in HMM. And I guess deviations from this usually indicate that there's something wrong with your state-dependent distribution, so something wrong with your observation model, whether it's you're not using a good distribution, so maybe the gamma distribution doesn't fit your data very well, maybe you need more states, something like this. It's typically a problem with the observation process. Okay, another thing that we can look at is the autocorrelation of the residuals. And so keep in mind, this isn't an autocorrelation function of the data itself. It's of the residuals. So it's autocorrelation once you've accounted for all of the covariates in your model. And yeah, basically, we want this one to be all the way down at 0. We don't want any autocorrelation. But this is really typical to still have autocorrelation left in HMMs. And yeah, it could indicate a violation of that conditional independence assumption. Okay, another way that people sometimes do model checking is to use simulation-based model checking. And so it's basically simulating movement tracks from your model and comparing the observed and simulated data. And so sometimes you can see that you're really obviously missing something in your model. Whether or not it's something that you actually care about capturing is maybe another question. But so this is I actually think a subset of the elephant seal data, where they're central place foragers, so they're going out from their colony, foraging, and coming back, and whatever model was used is not capturing that that bias or that kind of spatial component. So it's another way that you can think about diagnosing your model. And so obviously model checking is important. We want to kind of know what we're missing. We might want to know what assumptions we're violating. But I mean, we're never going to capture everything, and it's often the state classification or the Viterbi sequence is pretty robust to some assumption violation and some kind of model misspecification. And HMMs are a pretty complicated model. It's probably going to be impossible to include everything, like including an autoregressive process and covariates on all of your observation parameters and your transition probabilities. There's going to be a problem with estimability at some point where it's not really practically feasible. And so just kind of doing the best that we can. And again, I know it's going to be a little bit frustrating, but I don't have like hard and fast rules about what is acceptable and what's not. It's yeah, it kind of depends on exactly what you're trying to capture and how that's being affected by assumption violations and whatnot. Okay. Are there any questions? No? Either I explained things perfectly or people are like so confused they don't even know what the question is. Yeah.
So far we have not included any like between individual variation in these models. So like we assume that all individuals will behave the same.
Yeah. I mean, you could start to include some inter-individual variability if you had covariates on your observation parameters or your transition probabilities. Like if you had the age of the animal or the sex of the animal, that would start to capture it. But yeah, so far we're just pooling all of the individuals together. And
so in that case, the model doesn't consider, like, if I want just capture maybe the personality of the individual and somehow I don't have like a covariate for that. I have like the idea of the individual and try to understand how it's different their behavior from another one. Can I use the idea of the individual? Because you already used the idea of the individual to the model because you have 7 animals and there's everybody like making the same decisions for creating the model and where they're working or creating the states. So I can add again the idea of the individual as a covariate to see if there's a difference in how each individual decides to influence the states that are being selected. I don't know.
so you could add like a fixed effect of ID on your transition probabilities or your observation parameters. So so you could do that, and then you would estimate coefficients for each individual, which depending on how many individuals you have could end up being a lot of coefficients. It also would assume that the individuals are kind of completely independent. One thing that I'm not sure we'll have time for today, but there is the option to include random effects in an HMM. So we're assuming that there's some population mean, and each individual kind of varies from that, but they're all kind of pulled towards a population mean, whereas having a fixed effect, everything's just independent and they're just completely different coefficients. Is that?
Yeah.
Yeah. Okay. Okay. So now we're going to talk about, sorry, it's getting late in the day. Covariates. So I'm reloading the data. I'm going to re-prepare the data. This actually isn't going to make a difference, but it's just to point out that in momentum, if you have covariates that you're going to include, you can enter them using this cov names argument. And so here I'm going to work with distance and day, so I'm entering those. Here it's not going to make a difference, but if you have any missing covariates, so you can have missing observation variables but you can't have missing covariates, at least not on the transition probabilities. Because if you have missing observations, the model's still going to calculate a transition probability at each time step. And if you have covariate, or if you have missing covariates, it can't do that. So you do need to have all of your covariates filled, if they're covariates from the transition probabilities anyway. And so by default, if you have any missing covariates, momentum will take the closest covariate value and fill it. So if you don't want it to do that, you would need to somehow come up with a way to either split your tracks or interpolate it yourself in whatever way you want. But just to make you aware. It will pop up a warning, I think, that telling you that it's doing that, so you won't be without warning. But okay, so I'm going to, again, for simplicity, use gamma distribution and von Mises again. Sorry, just let me think about this for one sec. Okay. So I'm just going to refit. This is the same model that we fit in the last tutorial, but just for comparison for model checking and outputs. So this is nothing new, but I'm going to show you the pseudo-residuals of that model. So sorry, this is the two-state model with no covariates. And so this is what the plot pseudo-residuals function will give you in momentum. And so these are the pseudo-residuals plotted over time. And so we typically don't really want to see a pattern in this. It should just be kind of like a random scatter. Again, we want these residuals along this one-to-one line for the QQ plots, and we don't want to see autocorrelation in the autocorrelation function.
So these plots are fine, even our diagnostic or not? Are we happy or not?
I mean, you can see that like here in the step length distribution, there's some deviation. So I can never remember for QQ plots what that indicates. I think there are kind of like some rules about the shape, whether it's like left skewed or right skewed. I'm guessing this is something in the tails of the data that isn't quite being captured. So kind of in the extreme values, something isn't quite being captured correctly. These aren't horrible. I don't know. I've seen way worse. There's potentially a little bit of pattern here. There's some autocorrelation here. They're okay. I don't know. Probably could do better, but they also don't look terrible.
So I have a question here. We do that to make sure we can fit the model, right? So
No, so we've fitted the model,
yeah.
And so these are just like if you fit a linear model,
Yeah.
and then you look at the residuals after, and it kind of gives you an indication of how well your model fit.
Okay.
This is the exact same thing, but for an HMM.
Okay.
Does that make sense?
Yeah.
And so this was the model that we fit last time. It was just to show you the pseudo residuals. Okay, but now we're going to fit a two-state model with transition probability covariates. And so I'm going to set a transition probability formula where the transition probabilities are being modeled as a function of distance to the seal's colony. And this cosinor function is a momentum thing. It basically fits a harmonic of time of day, or sorry, this is day of year. A harmonic is basically a function that it's useful for cyclic patterns because it ensures that the beginning and the end match up. So if you have a time of day, it'll ensure that the function matches up when you switch from midnight to just after midnight. Does that kind of make sense? Because you wouldn't expect that if you had a really high transition probability at midnight, you wouldn't expect it to all of a sudden drop because it's a cyclic thing. So we want it to match up. And so a harmonic is one function to do that.
And this is cosinor.
Cosinor, yeah. So it's actually like the sine of the day of year times pi, or I can't remember the exact formula, but it'll fit like this, this function that looks like this. And yeah, Cosinor does that kind of under the hood, so you don't have to specify all the equation for the harmonic. But you do have to let it know what the period of your covariate is. So if you have time of day, it would be 24 hours. 24 hours, this is day of year, so it's 365. But it could be for any cyclic covariate. Oh, and one kind of nice, potentially nice function in momentum is it actually has a function called getParNot, which allows you to use the estimated coefficients from a simpler model as the initial parameters in your more complicated model. So that was another reason that I fit that model first. So this is the two-state model with no covariates. And so you give it that as an input, and then you specify what your new formula is. Did I run that? And so it's going to use the previously estimated coefficients as the initial parameters in your next model. So it's like better initial parameters potentially. So and I just wanted to show that these are identical. So it's using these parameter estimates. Okay, and so now we can fit this model. We're specifying PAR-naught as, so PAR-naught will be the initial parameters for your observation model, and that's stored in the output of getParNot as the par. But then, because we have transition probability covariates, we also need to specify initial parameters for those betas, and so those are also stored in this. Here, I can show you what it looks like. So these would be the initial parameters for the transition probabilities. These are the estimated transition probability coefficients from the previous model, and then it's just setting everything else to 0. You could set it to something else if you had a reason to do so. Does that kind of make sense? It's just a way to kind of automate setting initial parameters. You like that? And I think often for kind of regression coefficients like this, it's often reasonable to just set them to 0 if you don't have a reason to think that, a strong reason to think that they might be negative or positive. Yeah.
What if you had categorical coefficients, like male, female, or something?
Well, so then, I mean, you would specify that the same. You would have a categorical variable in this formula, and then you would have a coefficient for every category relative to the reference. So one fewer than categories that you have. Does that make sense? Oh, and I'm not using retry fits this time, just for speed. Okay. So these observation parameters are really similar to the previous model. We typically don't expect the observation parameters to change that much with covariates on the transition probabilities. This is going to be awkward to get through. Okay, so now when we use the kind of generic plot function, it's going to plot our state-dependent distributions, but it's also going to plot the covariate effects. This isn't working. Why isn't this working? Because it's not big enough. Oh. Do I have to like make this big? There we go. So this is for day of year. And so this is kind of hard to read, especially since we have such high state persistence that everything's kind of clustered either at the top or the bottom. So it's kind of hard to see the covariate effect here. But that is showing the covariate effect on the transition probability to stay in state 1, to switch from state 1 to 2. So this is showing that, I don't know, what is this, day 100, it's slightly less likely to switch from state 1 to 2. But like I said, it's really hard to see in these plots. Oh, and I just wanted to print this to make the point that now we don't get a single transition probability matrix, but you can get the transition probability matrix for a given time step. So this is for the first time step, but it would be different for every single time. And so those transition probabilities were a little bit hard to, I guess so far I've been kind of ignoring distance, but this is the stationary state probabilities for day of year. And so this is kind of the, we're seeing that it's more likely to be in state 1, kind of in from day 100 to day, I don't know, 200 or something. And then it's more likely to switch into state 2 at the, Jesus, in like the fall. I don't know what this day actually represents in terms of season. I'm like trying to calculate it in my head. But we can also see the same thing for distance. I kind of forgot I had 2 transition probability covariates. So this is showing that as they get further away from the colony, they're more likely to transition into state 1, which is that slow state, which is what you can see when you look at the map. So they're more likely to be engaged in that slow, kind of probably foraging state, further away from the colony.
One question. So that would be the probability of staying in that state. So the part, let's say you have state 1 and state 2.
So it's the probability. I meant to zoom this.
Would it be the orange one, the probability that they on the way to that state 1?
So this is saying that when they're 4 kilometers away from the colony, there's, I don't know, what is this, an 80% probability that they're going to be in state 1?
Yeah.
And there's only like a 20% probability that they're going to be
Right.
in state 2.
For example, if we instead look over time only for the first state, you see that there is a higher probability that they stay in state 1 the farther away from the colony. Like, if you assume that the orange one is a bit increasing, for example.
Well, it's a little bit of a, I think the stationary state probabilities are a little bit of a funny thing to interpret, because it's basically saying that if an animal stayed at 4 kilometers away from the colony forever, they would spend 80% of their time in state 1. So it's kind of like, if they stayed 4 kilometers away forever, you would still expect them to transition into state 1 or state 2 20% of the time, but most of their time would be in state 1. Yeah.
On top it says day 157. What is this?
Oh yeah, good catch. So because there's two covariates on the transition probabilities, if you plot these, it's going to set the other one to its mean. So you need to fix the other, just like in a regression model, if you want to predict the effect of one thing, you need to set every other covariate to some value. Yeah. And so I think by default it does the mean, but I mean.
Okay, so it will be the mean of the other covariates.
Yeah. Sorry, good catch. Okay. And so now we can't actually get the stationary. We can't use the stationary because we have stationary function because we have covariates in the transition probabilities, but we can calculate time in states, which is going to take the Viterbi sequence and then calculate the proportion of time in each state. Which actually, it's not that much different between the model. This is the model with covariates, this is the model without covariates. And again, I think that's pretty typical. We don't actually really expect the transition probabilities to change the state classification that much. It's just kind of how, it's just showing kind of what affects that state classification, if that makes sense.
Question.
Yeah.
Can
I know one of the assumptions is the covariates are indefinite with each other, but I can put in a model as you, I'm assuming if we make this here, like I put in a combination of distance and day. So I can run a model just with days and just with distance and day and compare these three models somehow like using AIC.
You could, yeah. Yeah, so you could put different covariate combinations and compare the models with AIC, and I think that that is a valid use of AIC for model comparison.
Okay.
And so we really don't want to use AIC for comparing models with different numbers of states, but it's fine for comparing different covariate combinations.
So I can put a lot of different models combinations between each other and arrange them with AIC.
Yeah, yeah, yeah. So that choosing covariates, I think the model selection would be quite similar to other regression model techniques. Yeah. Okay, I think here I just wanted to make the point that, like I mentioned, we can't just get a single stationary distribution. So this is the model without covariates. We just get a stationary distribution, whereas with covariates, you get a stationary distribution for each time step given the covariate values of that observation. So if you run this on a model with covariates, this is what it'll give you. And these are the pseudo-residuals. And so we didn't actually change anything in our observation model, so it doesn't actually really change anything in the residuals that we're looking at. Okay, any questions about transition probability covariates before we move on to observation parameters? Okay. So I know I kind of cautioned against using a lot of continuous variables and observation parameters, but for illustration, I'm going to model the mean step length as a harmonic of day of year. So it's basically going to say that what the slow movement state and the fast movement state look like depends on the time of year. I'm not saying that this is a great model for this data, but it's the assumptions that we're making with this particular model formulation. And so we can do the same thing with get par naught, where we can use the model with no covariates to get new initial parameters. Here, instead of using, I think it's formula when it's transition probabilities. Yeah. It's DM when you're looking at observation parameters. I think it stands for design matrix. I think that's why it's DM. But yeah, you would put your observation formula in there. So you can see that we're modeling the step mean as this cosinor function of day of year. And then again, these are, here I can pull up what these look like. So these are going to pull out, or going to use previous estimates to specify initial parameters. These are going to be quite difficult to interpret, these actual coefficients. So I'm not going to really talk about it too much, but nothing changes with the turning angle because nothing's being modeled as a function of covariates. And then again, we can use the transition probability estimates from the previous model as initial parameters in our next model.
The previous model, even the one that doesn't have covariates in the observation.
Sorry, it's the model with no covariates.
Okay.
Yeah. Because that's kind of the simplest model to build from. Like, if we also had transition probability covariates, like if we wanted to combine the transition probability covariate model with the observation, then we could use the initial parameters from the second model, but we're not doing that.
Sorry, what is the difference between the second and the third?
So the second model had covariates on the transition probabilities. So the modeling the probability of switching between states as a function of distance and time of day. And so now we're modeling the mean step length within each state as a function of day of year. So
what's the biological reasoning of having a covariate on the mean of the step length, for example. You said that at the beginning, but I don't remember. Like, why would we do this? But, well, what are we trying to grasp in the reality?
Yeah. So I think it would be when you assume that there is a single behavior, but there's some variability within that behavior. So you might think that an animal is still traveling, but its traveling state looks faster, maybe during a part of the year that it's migrating or something. Like it's moving, it's still, well, no, that's a bad example because migrating and traveling would probably be different states.
No, but here, like within the.
I think one that I like to think about is using something like the age of the animal or the sex of the animal, because I think it's reasonable to think that, well, both females and males forage and travel, but maybe males, when they travel further, they like take longer steps. And so if you put a covariate of sex, then you can capture that this is still biologically the same behavior, but it looks different for different demographic groups. Does that kind of make sense? I wish I had like an age or sex covariate in this data. It would have been a much nicer example to show, because I don't really have a biological justification for this model formulation. It's mainly just to illustrate how you do it and how you interpret it. Oh yeah, so these would be if you look at the coefficients, these aren't really that interpretable because it's like this cosine and sine functions of day of year. So I wouldn't try to interpret these. It's really the combination of them that gives the shape of the function. And then these would be the turning angle parameters. So we've looked at these now several times for several different models. Okay. Okay, so if we use the plotting function again, we can look at the state-dependent distributions as always. But then we can also look at the effect of day of year on the mean step length in each state. So state 1 is that slower traveling state, and so this is basically showing that kind of in this middle part of the year, the mean step length within the slower state is even slower. So it's kind of capturing temporal variability within that slower state. And we can look at the same thing for state 2, and it's actually the same pattern. So both states are kind of slower at the middle point of the year. But this is still, if you kind of look at the range of these, they're still, I think, probably separable states, but I think it's a little bit hard to interpret.
Could it happen here something similar to what you showed us before, that actually when you're like that it almost goes into the other state. Like let's say that you're looking at the variation of the step length within this state, and like very late in the day or very late in the year, that state is almost transitioning, or it's almost fading into the other one. We're saying that there is a risk that the two behaviors are fading to each other when you look at the covariance within the.
Yeah, so I think you can end up, depending on exactly what your effect is, I think you can end up kind of increasing the overlap between states depending on exactly what the effect is. This one, because it's the same, like, I guess one way that you could think about this is and maybe this won't clarify, but I can try, maybe it'll make sense to somebody. This would be saying like at day 200 in state 1, their movement follows a gamma distribution with a mean of 8.5. And so that distribution there would change, whereas at day 0, it follows a gamma distribution with a mean of 10. So it's like you can actually think about it as it follows a slightly different distribution at different days of the year. Does that make sense?
Maybe it gets more similar to the distribution of the others. Like
yeah, I think
more similar, like the mean and the standard deviation get more similar.
I think it could, like if you had something a little bit weird, particularly if the covariate effects were opposite, it would almost imply that maybe you're starting to mix up the states. Whereas this one, because they're both going the same direction, so they're both getting slower at the same time, the state separation, I think, is kind of being somewhat maintained. But I think you could end up with cases where they start overlapping more at different times of year or something, and that I think would be problematic for interpretation. And I don't think it would actually be like a biological effect. I think it would be like a modeling, like it doesn't make sense or something, like your estimates don't make sense. So I think that would be kind of up to you to interpret and kind of assess whether or not you think it represents something reasonable. Okay. It's really hot up here. You could turn it down to 22. So again, I'm just going to plot the pseudo-residuals. And I think there's actually less of a difference in the autocorrelation than I would have expected. I think when I fit this model, I was hoping that it would capture some of the autocorrelation. Oh, that's really small. I should zoom. I was hoping that it would capture more of the autocorrelation, but it actually didn't really have that much of an effect. So that was the one, sorry. This is with no observation covariates, and this was with the observation covariates. So they look actually quite similar. Sometimes you can see that autocorrelation drop when you start putting in covariates that are captured. The QQ plot got better. Slightly, yeah. Slightly better. And so because here we're actually changing the observation model, so the state-dependent distributions, sometimes we do end up with, I think, a bigger difference between the time and states, because we're actually kind of changing the definition of what those states look like. Whereas the transition probabilities, we're not actually changing the definition of the states, we're just modeling how the state switches occur. Okay, so that's all I have for that tutorial. I do have other materials, but I feel like this was a lot. And so, and I'm also actually starting to lose my voice. So I think my preference would be to, I don't know if it's too early to leave it. I mean, I could answer more questions if people have them.